TRAPPIST-1. You've probably heard the name. This small red dwarf star, just 40 light-years away, is a favorite among astronomers with its 7 Earth-sized planets. What's more, 3 of these planets are located in the famous habitable zone, where life could potentially exist. But there's a problem, a huge one. TRAPPIST-1 is not a calm host. On the contrary, it's an incredibly active, violent, and chaotic star. The massive eruptions on its surface, known as stellar flares, along with magnetic storms and starspots, constantly bombard its planets with radiation. Even worse, this activity was like a veil of fog, obscuring our view whenever we tried to study the planet's atmospheres. Until now. Thanks to the James Webb Space Telescope, astronomers have not only pierced this veil of fog, but they've turned it into an advantage. They used the star's greatest flaw as a key to unlock its biggest secret. If you're ready, let's see how a star's fury has forever changed our quest to understand its planets. First, let's understand the problem fully. TRAPPIST-1 is an M8-type ultra-cool dwarf star, much smaller and cooler than our Sun. But don't be fooled by its size. Its magnetic activity is extreme. This means its surface is constantly covered in starspots that are much larger and more persistent than the sunspots on our Sun. These spots are dark regions, several hundred degrees cooler than the rest of the star. When a planet passes in front of its star, or transits, we analyze how the starlight changes as it filters through the planet's atmosphere. By looking at which colors of light are absorbed, we try to figure out if there are gases like water vapor, methane, or oxygen in the atmosphere. This is where the star spot problem begins. If a planet passes over a spot during its transit, the profile of the light reaching our telescopes changes completely. This spot can make it look like a gas is present in the atmosphere when it isn't, creating a false signal. Or it could do the opposite, masking the real signal of a gas that is actually there. For years, astronomers had to use models based on assumptions to solve this stellar contamination problem. But no one knew the exact light signature of TRAPPIST-1's spots. This is where everything changed. A research team from the Max Planck Institute pointed the James Webb Space Telescope at TRAPPIST-1 and waited. Their goal was to catch one of the star's most violent moments. And they succeeded. 4 times. The telescope recorded 4 massive flares erupting from the star second by second. Using a technique called time-resolved spectroscopy, they watched with incredible detail how the star's light changed before, during, and after each event. And then they noticed something strange. After each massive flare, the star became permanently brighter at certain wavelengths of light. At first, they thought it might be a lingering afterglow from the flare, but the data didn't match. This brightness lasted much longer than the flare itself. And then came the eureka moment. The flares were so powerful that they had disrupted the magnetic equilibrium on the surface, essentially wiping the dark star spots clean, like a brush. The star's surface had been, in a very real sense, scrubbed clean. This was a goldmine for astronomers. They now had 2 different scenarios in their hands: the spectrum from before the flare, with a spotty surface, and the spectrum from after the flare, with a clean, spot-free surface. By subtracting one from the other, they captured the direct, flawless fingerprint of a starspot on an M8 dwarf for the first time in history. So what does this mean? Everything. Astronomers can now perfectly subtract this spot signature from the data they receive from TRAPPIST-1's planets, just like removing a variable from an equation. This means false atmospheric signals can be almost completely eliminated, and real signals can be seen with much greater clarity. We now have our best chance ever to get reliable data on what's really in the atmospheres of those 3 planets in the habitable zone. But the impact of this discovery isn't limited to TRAPPIST-1. This is a revolution in methodology. We now know that the violent flares on red dwarfs aren't just an obstacle, they're an opportunity. Astronomers can now deliberately wait for a flare to occur when observing other active stars. These flares reset the star's surface, giving us the key to solve the mystery of starspots. We can use the same technique to study the planets of other famous red dwarfs, like Proxima Centauri. This work transforms stellar activity from a problem into a tool. The very explosions that once obscured our view have now become a beacon, providing the clearest sight. Unlocking this secret of TRAPPIST-1's magnetic field is a giant leap forward, not just for the fate of 7 planets, but for solving the atmospheric mysteries of countless planets orbiting the billions of red dwarfs in our galaxy. In the search for life, we have seen once again that the biggest obstacles sometimes hold the most unexpected solutions.